Alright, good evening folks. Welcome back to yet another exciting video. This video is on vectors. Let's look at this question. The position vectors of the points P, Q, R relative to an origin O are, well, it's those vectors respectively. Part 1. Calculate the value of, well, this symbol means the magnitude of vector OP. Now before we start, let us observe that this question is a position vector, meaning it is relative to an origin O. So what we're going to do, we're going to put everything in order. So P, Q, and R are, these are the corresponding column matrix or vectors. All right, so I'm going to write them as this: OP, OQ, and OR. Now it's worth noting that PO would be the inverse of vector OP, and the inverse of vector OP is 3 and -4. Likewise, OQ, the inverse of OQ is QO, that's -1, -1. Inverse of OR is RO, that's -5 and +2. All right, so we will just have this information down for future reference. All right, so let's get to the question. So the formula of finding the magnitude of a vector is this. So it is x squared plus y squared, and we find the square root of that. It's pretty much similar to what we call Pythagoras theorem. Since we're dealing with OP, and OP is related to -3 and 4, so the -3 would have been the x, and the 4 would have been the y. Remember, in a vector, the top number represents the horizontal shift, and the bottom number represents the vertical shift. All right, so it's going to be square root, so that's going to be -3 square plus 4 square, and -3 square is -3 multiplied by -3, which is +9, so put 9 there. 4 square is 4 times 4, which is 16, and we end up with the square root of 25, and we know the square root of 25 is 5, so the answer is 5 units. All right, let's move to the next part of the question. It says express in the form xy the vectors pq. All right, now to find pq, we're going to write the vector equation. Now I did mention previously that this is a position vector, meaning that everything goes to the center. All right, so let me give you a little let me give you a little view of what a position vector is, right? So let's say you have a little grid here. All right, and let us say we have these two vectors, OA and OB. All right, now what if I want to go from, say, A to B? What I'll have to do is to go from A to O and O to B. So the vector equation for AB would be A to O and O to B. So what do you notice? We always go to the where? The center. So if I change these two letters here, these vectors, let's call it P and let's call it Q. The vector equation, as long as it's a position vector, it would be P to O, P to O, origin, and then O to Q. So based on what I said a while ago, the vector equation PQ would have been P to O and O to Q. All right. Now we know what OP is, right? But this equation is asking us for what? PO. PO would have been the inverse vector of OP. No, PO would have been 3 negative 4. So we're gonna have 3 negative 4, and then OQ, O to Q would have been 1 and 1. And like a matrix, we add corresponding entry with corresponding entry. So we're gonna add 3 plus 1 and negative 4 plus 1. And that will give you 4 and negative 3. So this would have been P to Q. Let's do the other one now. The other one is Q to R. So what we do, we're going to write a vector equation. Now, what type of vector is this? It's a position vector, meaning that it's going to always go to the center. So to write the vector equation for QR, we would have written Q to O plus O to R. Now, we know that O to Q is 1, 1. So Q to O will be negative 1, negative 1. It is the inverse vector. So we're going to have negative 1, plus OR, and OR, see, R would match up with this. So OR would have been 5 and negative 2. So that's 5 and negative 2. And we're going to add those matrix, entry by entry. Negative 1 plus 5, negative 1 plus negative 2. All right. So we know that the top one is going to be positive what? 4. Now right here is a little bit tricky. Now you notice we have two signs together. All right. And when we have two signs together, we're going to use the rules of multiplication. So a positive and a negative will give you a negative. Let's write back the 2. And then we work out this. No, we owe and we owe. We owe 1, we owe 2. So we owe 3. All right. So this question has a third part. This question has a third part. It says using the results in part 2. All right. So all of this is part 2. Part 2 says to find expressed in the form xy, pq, and qr. So this question says, using the results in part 2, justify that pq is parallel to qr and that pqr is a straight line. So now to prove that two lines are parallel, two things. One, we can find the gradients and compare them. If two vectors have the same gradient, then the two vectors are parallel. Or if we can find a scalar multiple of the other vector, then the two vectors are parallel. Let's just check their gradients. Now we're going to find the gradient gradient of PQ, of the vector PQ, and that formula is just y divided by x. Now PQ is actually 4, -3. So if PQ is 4, -3. Now remember we said that the top number is the horizontal shift, which is x, and the bottom number is the vertical shift, which is y. So if the formula is y over x, it would have been -3/4, or you could say -0.75. All right, so that's the gradient for vector PQ. It is -3/4 or -0.75. Let us check out now the gradient of QR. Now Q to R is also represented by the same value. All right, turns out that these two values are the same, which is 4 and -3. So QR is 4 and -3. All right, and the formula for gradient, so the gradient of QR is y divided by x. Now we said that the top number would have been the x value, the bottom number would have been the y value. So that turns out to be -3/4 or -0.75. Now what do you notice? Both of them have the same one, gradient. So we said that the two vectors are parallel. So since both vectors, and we're talking about PQ and QR, have the same gradient, then both vectors are parallel. Now if both vectors are parallel, it would have mean that the points P, Q, and R would lie on the same line. In other words, they are co-linear. All right, now we said that there's another way of proving that two lines are parallel, and the other way is to show that one vector is a scalar multiple of the other vector. All right, so let me just briefly look at that. So I'm looking at the other approach of proving that two vectors are parallel. So we said that we need to show that one vector is a scalar multiple of the other. Now PQ is 4 and -3, right? And QR is 4 and -3. So what can we say about these two vectors? We can say that, well, both of them are equal, so PQ is equal to QR. But actually, in fact, one is actually a scalar multiple of the other. The scalar multiple would have been 1. All right, so you could have put the 1 beside the PQ or the 1 beside the QR. Let's just put it beside the QR. So what do you notice? QR is a scalar multiple of the other. So therefore, PQ and QR are parallel. Mind you, this could have been 2, 3, 4. It could have been a quarter, 3/4. It could be any fraction, as long as it's a scalar multiple of the other. All right, folks, that's it.